Welcome to Newton's corpuscular theory of light. So we have Isaac Newton here on the left, and we have Christian Huygens here on the right. Newton was a British physicist born in the 1600s, and Huygens was a Dutch physicist also born in the 1600s. They both developed their own theories about the properties of light. Newton had the idea that light was a series of particles called corpuscles. Hence the corpuscular theory of light. Huygens developed a wave theory of light. Both of these theories could explain wave reflection, wave refraction, the dispersion of light, but only Huygens' wave theory could explain diffraction. Newton's corpuscular theory could not explain this phenomenon. Let's have a look at Huygens' theory more closely. So Huygens had the idea that light is emitted from a point source, or potentially a source that is composed of multiple point sources. And it emits spherical waveforms. So you can see that this point here at A is emitting this wavefront, etc. And this point B and C are also emitting spherical wavefronts. And as they overlap and interfere, you can see that the wavefronts are combining to produce an overall spherical wavefront being emitted by this candle. Huygens used these ideas to explain refraction. Now, when a wave refracts, it approaches an interface where it's going to experience a speed change. Now, in this example, it's going to slow down, and so it's going to bend towards the normal. Huygens explained this by telling us about the behavior of the wavefronts. He imagined that the point sources on the wavefronts are emitting spherical wavefronts that have a certain radius, and that radius depends on how far the wave is moving per second. And what's going to happen is that as the wave enters this new material and crosses the boundary, the wave is going to slow down, and that means that the wavefronts are going to end up closer together. When the wavefront approaches at an angle like this, one side, this side, is going to enter that material before the other. So this side of the wavefront is going to slow down first. And as it does so, it turns toward the normal. And that's because this point source is now emitting a smaller radius spherical wavefront compared with a point source over here, causing these flat wavefronts to bend toward the normal. Huygens was able to explain reflection in a very similar way. Here is the mirror surface, and here are the wavefronts approaching the mirror. And what they do is when a point arrives at the mirror, instead of the wave propagating further into the material, it is reflected from the surface. And here. And so what happens is that the approaching wavefronts are simply reflected from the surface. Their direction of approach is reversed. Instead of propagating into the material, they are being transmitted outward, and you have the effect of reflection. Let's have a look at Newton's corpuscular theory of light. So In order to explain reflection, Newton had the corpuscles approaching a reflective surface and then simply rebounding, bouncing off that surface. His theory about refraction was very different, and he had to come up with some ideas that do not hold true nowadays. So if we examine one corpuscle and we see that it is travelling with this velocity here, what we can do is we can resolve that into a horizontal and a vertical component. So let's draw those on now. There is the horizontal component, and here is the vertical component. So we have a resultant in this direction, and the corpuscles move towards the interface between the two materials. When a corpuscle meets that barrier, and this material is, say, glass, and the material above is something like air, he proposed that the corpuscles would travel faster in a more dense material. And it does that by experiencing a force dragging it into the material. And what that force effectively does is increase the velocity in this direction. And meanwhile, Vx is unchanged. So we now have a resultant that is pointing more towards the normal than it previously was. So we can see that the light ray would be bent towards the normal, just like we see in refraction. So his theory was that the material was pulling the corpuscles in, and they were speeding up as they entered the material. This is very different from Huygens' theory, where the wavefronts are slowing down as they enter the material. One thing that Newton's theory could not do was to explain diffraction. And here is Huygens' idea of how diffraction can occur in wave theory. So what's happening is that we're having flat wavefronts approaching a gap, and these point sources along the arriving wavefront are each emitting spherical wavefronts. Those in the middle are combining, just like they did before, to produce a flat wavefront. But because we are losing this part of the wavefront over here and over here on the edges, then the point sources on the extreme ends are producing a spherical wavefront, and there's nothing to cancel those out and flatten them. So we end up with that spherical part of the wavefront being maintained here and here. Newton's theory does not explain diffraction. And yet the scientific community went with Newton, his theory of corpuscles, and dismissed Huygens' theory of waves. And this is because at the time Newton was a very famous, a very prominent physicist, and he had a lot of influence in scientific society at the time. Now, up until this point in history, scientists were familiar with the idea of waves. They were aware of water waves, for example, and they knew that waves needed a medium, a material, to travel through. So it was proposed that Huygens' waves would travel through a material that had zero mass called luminiferous ether. This is often shortened to ether, and sometimes the spelling is shortened to ether beginning with an E. We will be studying a very famous experiment that tried to prove or disprove the existence of ether, but that's in another video.